about?
On here it says I've got some of these turned in.
Mm-hmm.
And then it says they're missing.
Well, see me at the end of class. We'll talk about that. All right, guys. So today we're going to cover Chapter 3, Part 3, which is Properties of Logarithms. So Chapter 3, Part 3, Properties of Logarithms. Here are all the standards. So basically, I want you to apply properties of logarithms to solve equations and simplify expressions, and then use them in real-world problems. So some applications. When we discover a fossil as a scientific community, you guys familiar with the Great Fossil Site? So sometimes they'll find interesting fossils and they have to date them. So they date them by the process of radiometric chemistry. So radioactive isotopes decay to their stable form. Carbon-14 is an example. It decays down to carbon-12. So carbon-14 in nature has a certain ratio to the stable form. And once something stops interacting with the environment, it stops taking in the radioactive isotope. So it starts to more and more decay to the stable form. So you can look at the ratio of the radioactive isotope that occurs in nature versus the stable form of the chemical and get a good idea about how old it is. Now, these types of radioactive clocks vary greatly in their application. Carbon-14 is used for very recent fossils, things in the last few tens of thousands of years. Its half-life is about 5,000 years. You have other things like potassium argon that are good for much, much older fossils. So anyway, that's an application of the logarithm. The formulas that we use to determine the age is a logarithmic equation. So this is the definition of the logarithm, which you wrote down yesterday. Logarithm base b of x equals a, meaning the power you put on the base to get the argument is this a value. So the power I put on the base to get the argument is a. All right, so 3 primary rules for exponents. So this is a bit of a review. Remember your 3 major rules for exponents. They are the product property. If I have the same base and I multiply those together, I'll sum their exponents. If I have the same base and I divide them, this is the quotient property, I subtract their exponents. And then when I have the power of a power, I'll multiply their exponents for the power property. So make sure you're familiar with these. This would have been something you'd covered pretty thoroughly in Algebra 2, but it's related to what we're going to do today. Yeah, make sure you have these noted. When we were having our little discussion before class, we're talking about some of the challenges people face with online learning. And one of the problems is if you're entirely passive, in other words, if you're just sitting there kind of spaced out, not doing anything, you're less likely to learn. And that's true for in-person learning as well. So make sure you jot down this stuff, follow along with me, etc., etc. All right, so here are the 3 main rules for logarithms that logically follow from those previous rules. The proofs for these involve those formulas you saw just a second ago. So here's the main idea for this section. The product property of logarithms says the log base b of x times y equals the log base b of x plus the log base b of y. In other words, if I have an product in the argument, I can rewrite that as a sum of 2 separate logarithmic terms. Now, if I have a quotient in the argument, for the second one here, I can rewrite that as a difference. So a quotient can be rewritten as a difference of those 2 the numerator and denominator. Divisor, dividend, whatever. And then finally, the power property allows me to write any exponent in the argument as a coefficient. That's a little too dark. So when I have a product in the argument, I can rewrite that as a sum. When I have a quotient in the argument, I can rewrite it as a difference. And finally, when I have an exponent in the argument, I can bring that out as a coefficient. Okay, any questions about that? I need a second. Okay. Again, the main idea of this section is here. So a quick proof of the product property. You don't have to write this down, just to let you know how those two formulas are related. So consider log base b of x times y. So this was the product property, the left side of that product property for logarithms. If we let x equal b to the m, so b is some legal exponential base, that means b to some power m is going to be equal to x. And y, b to some power n, is going to be equal to y. So I can rewrite that original expression as log base b of b to the m times b to the n. And now here's where we apply that exponential property. Remember, when I have the same base, I can add the exponents. So the log base b of b to the m plus n. And then you remember, what power do I put on b to get b to the m plus n power? Well, that's just m plus n. And so that is the log base b of x plus the log base b of y equals log base b of m plus log base b of m equals m plus n. So this is equal to this. And so you have the product property for logarithms. Again, nothing I would give you on a quiz or a test. I just wanted you to know how those two formulas were related. So common logs and natural logs, you guys know all about that. Common log has what for its base, Colby? Good. And then what about the natural log, Allie?
Oh, sorry.
That's okay. What do you think the natural log's base is? Special number. We use a single letter for it. Not quite. What do you think, Clay?
I think it's any real number, right?
No,
That's just
the natural log has a specific base, and it's a special constant that we use a single letter to stand in for.
E.
E is correct, yes. E is the base of the natural log. So remember, the common log is base 10. The natural log is base E. Remember, which is about 2.718. So common log and natural log. Those are the ones that are on your calculator, and they're the ones that are most frequently used. A couple reasons why they're important. So let's do an example. First of all, a long time ago, it was important to consult tables. So when you were doing mathematics in the 1600s or 1700s, you of course didn't have a calculator. What you would have were these exhaustive tables. And they would want to make them as concise as possible to do the job. Like you couldn't have a table that would show the logarithm of every value. It'd just be too long. So instead they used prime numbers, and here's why. Because you can rewrite numbers in terms of primes. So let's rewrite these two logarithmic expressions in terms of natural log 2 and natural log 3. So this would have been the process that a mathematician of many centuries ago would have used to prep this expression for evaluation through a table. All right, so anyway, ln of 54, the natural log of 54. So what I'm going to do is use those properties we discussed to rewrite this And I want 2 and 3. So if I think about 54, well, that's 9 times 6. And so that's 3 times 3. And then that's 3 times 2. So what I've got is 3 squared times 2. Does everybody see why that's the case? Okay, so this is not a challenging thing. This is factor trees. You did this in 4th grade. Don't act confused by this unless you really are. And in that case,
I'm maybe incorrect, but there are 3 3s on the bottom, right? So would it be cubed, or am I just?
oh, thank you.
thinking that?
Yeah, you're right. I just wrote it wrong. All those 3s and 2s got the best of them. Thank you, though. All right, other questions? Okay. So your passivity has reached the point where it's difficult to teach you. So you guys are going to have to, wake up, pay attention. All right, so we're going to rewrite this as 3 cubed times 2. And then I'm going to use the product property of logs. And it's going to be the natural log of 3 cubed plus the natural log of 2. And then finally, the last thing I'm going to do here is the power property of logs. So I'm going to take this exponent and make it into a coefficient. And now we have accomplished the task, which was to rewrite that original expression in terms of natural log 3 and 2. Do you see how now, if we were an ancient mathematician, we could consult our little brief logarithmic table, find the value approximately for natural log 3 and natural log 2, then plug it in here and have a good approximation for this expression. But it was unlikely natural log of 54 would be on our table, unless we had a really huge table. I'll show you what one of those tables looks like real quick, because I've got an old book. My brother was cleaning out an old house once, and he found this book of mathematical tables. But yeah, it would just be these big long lists, one after the other, page after page of logarithms of certain values. All right. So questions about the first one? All right, you could reproduce this. Okay. So there's part A. Let's look at part B. So this is the natural log of 9 over 8. A little bit easier to factor here. That's 3 squared and 2 cubed. 3 squared is 9, 2 cubed is 8. So we're going to now use the quotient property of logarithms, which is going to give me the natural log of 3 squared minus the natural log of 2 cubed. Notice the difference between the product property, it was a sum. When I simplify using the quotient property, it becomes a difference. Now I'm going to use the power property. And it's always good to indicate that it's the property of logarithms, because all these have analogous properties in exponents as well, which are more commonly used. So each of these exponents becomes a coefficient. All right. So stop me if you have any questions about any of that.
Do we always put it to where the exponents are quotients, or is it just for the problem?
Well, it depends on which direction you're simplifying. If you're what's called expanding the logarithmic expression, yes, you would always do it this way. If you're condensing the logarithmic expression, you would generally do the opposite. you'd start out with a coefficient and then you'd make it a exponent of the argument. But that's kind of getting ahead of ourselves. Okay, so if you look on page, yeah, so log 75. Actually, you don't have to look on anything. I've got them already. Wow, are you kidding me? So I use log 2 and 3. You're going to use log 5 and 3. Rewrite the log of 75 and then the log of 5.4. And let me give you a hint on 5.4. We're going to rewrite that as a fraction. So 27 over 5 is another way to say 5.4. If you're having trouble getting started, let me know, and I can help. 5.4. Or were you doing the second step of the first part?
I'm just going to do the first part.
Oh, okay. My bad. Yes, that's B as well. Yeah, the first step is right.
Okay.
There's one more step, which you've indicated here.
Okay.
Excellent. Very good. Well, it's 25 times 3. Yes. Yeah, it's not the sum, it's the product. So 1 times 1, yeah, so 25 times 3. And 3 is already prime. So you got yes. Easy mistake to make. Divided by 5. This should be difference. Okay, so that should be divided by 5. Yeah, the only difference is it'll be a difference instead of a sum. This I agree. It's law, not natural language. I don't need to change it. Yeah, so we must stick with whatever logarithm we're. In this case, it is the common log. So you just put an equal sign right there. Say log. And then the squared. And then the log here.
That's okay.
It's okay. There you go. Now, the very last step is going to be using this exponent coefficient. So you can put equals. And it's 2 times log 3. 2 times log 2 first. That parentheses 5. Plus LG3.
I don't want to go down here.
You might have to go up the margin on it. Yeah.
Thank you.
You're welcome. All right, so let's talk about this a little bit. Clay, what'd you get for A here?
I got 2 log 5 times log 3.
It should be plus.
Oh,
Remember that the product property takes a product in the argument and turns it into a sum outside the argument. So it should be a plus sign, but your terms were correct. Good job. And then Colby, what about the second problem here?
3 log 3 minus log 5.
Very good. So you'll notice sometimes I put parentheses around the argument and sometimes I don't. Generally, if it's a single value, it's not as important. But if your log has more than one term in its argument, you must use parentheses. So if you've got an addition or subtraction symbol inside the argument for a logarithm, you have to use parentheses in. Otherwise, it's optional. I try to be consistent. In other words, if I do it for one step, I try to do it for every subsequent step. Or if I don't do it for one step, I try to not do it for every subsequent step that doesn't absolutely require it. But anyway, parentheses are optional. If no parentheses are present, it's understood that whatever comes next, that first term following the log is its argument. Okay, so any questions about these? Have those guys got these answers? Yes, ma'am.
When you say that like another term is attached to that, what do you exactly mean?
Okay, so in algebra, when you have a polynomial, you can have one term, which is like this. That's a single term. But a multi-term polynomial will have something else attached with a plus or a minus sign. So this is multiple terms, and this is a single term. So if you've got a single term, you don't have to use parentheses. If you've got a multiple term for the argument, you must.
So what kind of problem would that be?
If I had like this, if all of this was the argument, the parentheses are not optional in this case. Or if I had something like this.
But you would solve it the same way with the
Yeah, it works the same.
All right.
Yeah, the only difference is the parentheses are not optional in this case. Good question. Other questions? All right. So let's talk now about simplifying an expression. So we're going to use the rules of exponents and logarithms to simplify these expressions here. So I've got log base 4 of 64, and then that's to the 1/5 power. So a couple ways we can do this, but one way that's really consistent with what we've learned today is to use the power property for logs first. And then I know that 64 is 4 to the 3rd power. So this is going to be 3/5. So between the first step and the second step, I applied the power property of logarithms, which allows me to take any exponent on the argument and move it out as a coefficient.
So you got 3 by dividing by cubing 4?
Yeah, because as I said, you should know the first few perfect cubes. So 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. That you probably won't see a whole lot of problems that don't that go beyond that to the third power. But anyway, yes, 64 is 4 cubed. So what power do I put on 4 to get 4 cubed? 3. And then that's where the 3 comes from. Okay, so for this next one, it's not labeled, but we'll call it part B here. Hey, Mason. All right. Overslept, dang. Okay, so we're going to use the power property for logarithms again, which tells us we can take any exponent on the coefficient, or exponent on the argument rather, and move it out as a coefficient. So this is going to be 5 times 2 ln of e minus 3 times ln of e. So the natural log of e, what power do I put on e to get e to the first power? Don't overthink it. The natural log of e, when the argument is the same as the base, what's the result? What power do I put on a base to get itself? 7 to what power is 7? 1. So e to what power is e? 1. So these both simplify to 1. And so I get 10 minus 3, or 7. Just kind of getting used to working with logarithms here. All right, so here's one for you guys. And so we'll give you a hint for this first one. Well, the third root is also to the 1/3 power. So see if you can use those same properties to rewrite this as a simpler expression. If you'd sign that, Macy, just saying that you know where to get your handbook. And this is your progress report.
Thank you.
Yes, you're welcome.
Thanks for being late.
It's okay. It happens. Yes, ma'am.
So, this one,
Because I knew 4 to the 3rd power is 64.
oh,
So in this case, you don't lose your base, it's 6. So what power do I put on 6 to get 36?
2.
So it's 1/3 times 2.
Okay. Okay.
Good job. Stop me if you're confused, can't figure it out. Need a prompt. As I had said on Friday, of course you guys weren't here, but logarithms often pose a cognitive barrier to folks. In other words, it's not intuitive. You'll have to constantly consult notes, and that's totally normal. Just we're introducing this fundamentally new concept very late in the mathematical game for you. If we had showed this to you when you were in 5th grade, this wouldn't be a problem. But they wait until you're 17 to show you this for the first time, or 16, whatever. And so it's, your brain learns very differently at this age than it did when you were younger. It's not ideal. Okay. Let's see what we think about this. Riley, what about part A here?
I want 2/3.
Okay, so that would be 1/3 times the log base 6 of 36, and then 1/3 times 2, and then you got 2/3. Were those the steps used? Excellent work. All right, and then Allie, what about this one right here?
I didn't get to that one. I'm sorry.
She was so.
That's okay, that's all right. Let's see, Mackenzie, what'd you get for this second?
I got -3.
So I think I know where you went with that, and just follow along with my steps here.
Okay.
And I bet I know what went wrong. I bet you wrote a minus sign here.
Yeah, I did.
Okay, so, and actually I got ahead of myself. So this is 9 times 1 plus 12 times 1. It should be a plus sign.
Oh, okay.
So that should be 21. Yeah, so only if have a quotient in the argument is that going to be a case where we'll use a difference. Because it's an addition symbol in the first step, it'll persist throughout. Other questions, thoughts? Okay. Remember, it's very important to stay on top of those videos. I know they're mind-numbingly boring in some cases. I do my best, but I don't have a production studio and a staff to help me with, making it more enjoyable. Got just for only. So, despite the low production quality, please try to give those a watch before you come in on Monday, because otherwise you'll be looking at material that's dependent upon what we've already learned, and you haven't seen that yet. And if you watch it after the fact, it's not as educationally impactful. Okay, so example 3. Come on, baby. So we're going to expand. Remember I told Colby something about expanding and contracting? So if we look at those 3 rules, and we'll write them here real quick. You've got the product property of logs, which goes like this. Log base b of x times y equals log base b of x plus log base b of y. And then you've got the quotient rule, which is log base b of x divided by y equals log base b of x minus log base b of y. And then finally, you've got the power rule, which is log base b of x to the p equals p times log base b of x. So in general, ladies and gentlemen, when we go from left to right, so when we start on the left side of one of these and we rewrite it as the expression on the right, this direction is called expanding the logarithmic expression. However, if I go the other direction, that's called condensing. And there will be times when we need to expand and times when we need to condense. So if we start with an expression like we see on the left and we rewrite it like we see on the right, we have expanded the logarithmic expression. If we start with something that looks like what's on the right and we rewrite it as what's on the left, we have condensed the logarithmic expression. So here we're going to expand. In other words, we're starting with something here, we're making it into something there. This is going to be quite a few steps. So my first step is going to be to apply the product property. So I'm going to rewrite this as the common log, no base, it's understood to be 10, of 12. Let me get this stuff out of the way. There we go. So the log of 12 plus the log of x to the 5th plus the log of y to the negative 2. Notice if I have 3 factors in the argument, doesn't matter. I can apply the product property of logarithms to an arbitrary number of things multiplied together. But this is not really the best way to write it. Even though it is a single term, there's so many factors, it almost sort of necessitates parentheses in this case. Just so you understand what's going on. All right, so now is when we're going to apply the power property. So, and you need to rewrite your argument in terms of primes. So I'm going to rewrite 12. That's going to be 4 times 3, which is 2 squared times 3. And so I'll go ahead and rewrite this term as 5 times log of x, and this term as negative 2 times log of y. So I applied the power property to these two terms. On this first term, I rewrote the argument in terms of prime numbers. And I'm going to need to apply the product property again. Yeah, these aren't done until it's not fully expanded, until only prime numbers exist in the argument. So this log of 12 would not have met that criteria. So last step, I'm going to use the power property again. To get this. So that's expanding the logarithmic expression. And again, that's something we might have done many years ago to compare to a table. Particular fascination of the current political generation is to judge our ancestors based on current moral standards. I think an interesting mathematical analogy is I could call Sir Isaac Newton an idiot for just not using a calculator. Why didn't he just use a calculator? Well, he didn't have one, of course.
Why didn't he just invent one?
Well, yeah, there you go. That's the exact question we're posing, isn't it, when we say George Washington was a bad person? Because he was confined by the morals and the norms of his time. Why didn't he just invent an entirely new morality and then adhere to it? Well, that's a pretty ridiculous question, isn't it? Why didn't Sir Isaac Newton invent the TI-83 calculator and then use that? Well, that's ridiculous. It's a non-linear jump, both in mathematics and morality. Okay, so back to this. Questions about this, anybody? Okay. Doing this because it's so small. I'll rewrite it before we begin. This time we're condensing, guys. So if we use this same, I'll just steal this. We're going from right to left this time. So 4 times the log base 3 of x minus 1/3 times the log base 3 of x plus 6. That 6 looks pretty innocuous, doesn't it? Looks like a harmless little constant term out there. It's really a headache when it comes to doing what we're about to do, and you'll see why in a moment. So we'll sort of go in the reverse order of last time. We'll start down here with the power property. And remember, we're going this way, so we're bringing these coefficients in. So this is log base 3 of x to the 4th minus, I'll just do these two at once, log base 3 of x to the 1/3. And then we'll leave 6 alone for a moment. Notice this is a difference. So I can use the quotient property from right to left to rewrite these two terms as the log base 3 of x to the 4th over x to the 1/3, which is also the third root of x. Another way to say x to the 1/3 is the third root of x. Those are equivalent statements. All right, now the plus 6. Let's finally do something with that bad boy. I need to rewrite that as a logarithm. So I need to know, and I need to use the same base. So the log base 3 of what equals 6? I want to rewrite this as a log base 3 term. Well, it's going to be 3 to the 6th power, right? So if I say 3 to the 6th power, that's 729. So I can rewrite this as log base 3 of 729. And the reason why I chose 3 is because that was the base over here. So we want to rewrite this as a logarithm of the same base as the other term. Now I can combine these with the product property, and I can say log base 3 of x to the 4th over the third root of x times 729. And last step here, log base 3 of 729 x to the 4th over cube root of x. And that one is pretty messy. Let me shrink this work down just a touch. Okay. Questions about that? That's expanding and condensing. So expanding is when we start with something that's pretty concise and we make it big. And condensing is typically where we start with a bigger expression and make it smaller.
Could you explain one more time for me how you got the plus 6 into log base 3 of 729?
Sure. So 6 is, we want to condense this. In other words, make it a single logarithmic term. And the only way I can incorporate 6 is if I rewrite it in terms of log base 3.
Yep.
So I had to pick a logarithmic expression that evaluated out to 6 and had 3 as its base. So that posed the question, log base 3 of what is going to equal 6? Well, that's going to be 3 to the 6th power. So this is going to equal log base 3 of 729.
Okay.
So I just had to rewrite it as a logarithmic term with the same base as the other terms I was dealing with. Good question. That's probably the trickiest part and an often missed test question. There's a test question that has a constant hanging out, and you've got to do this step. And pains me to admit, but many years ago, I got that one wrong on the key. So if I can miss it, you guys surely can miss it. I was corrected by a particularly intelligent student, Hannah Holtschult, who I think now is a traveling doctor with Doctors Without Borders. Is that the name of that organization? And she's in, I think, the Palestine. Pretty impressive young woman. But yeah, she corrected me for my mistake on the key, for which I was forever grateful. Okay, so here's one for you guys, or two rather. I want you to try both of these. So I want you to try to expand A and then condense B. So try to expand the first example and condense the second. As always, stop me if you're unsure how to begin. So those three properties listed are the fundamental ideas of this section. And in order to expand, we're going to be working from left to right on those properties, which you did. So you use the product property. Last argument is going to be C to the
Was it on this, do you need to be separate too?
let's see. Yeah, log base 13 of 6, log base 13 of A cubed, and then log base 13 of B. B should be the next one. Yeah. Now use your power property to bring out any exponents. So a logarithmic expression is not fully simplified unless every argument is a prime number. So we've got 6 there, which is actually 2 times 3. So we can rewrite that very first term as log base 13 of 2 plus log base 2 log the rest of it. Simplify.
So I need to do that with 4.
No, because it's outside of the argument. It's a coefficient, so it's okay.
Okay.
No need to do that.
Thank you.
You're welcome.
This one.
Let me see. Well, on that very first step, let me see the pencil. There's just one little boo-boo. Probably just. Okay, you see the first one's 6, and then it's 8. So the rest of it's right.
Okay.
And then for this bit, you treated that kind of like it was an exponent, but, so this is right, everything's right, but this log base 13 of 6, when you've got a non-prime number, you need to rewrite it as primes, which in this case is 2 times 3. So I can do that, and then you just rewrite those terms and you've got it.
Okay.
Yes, ma'am.
Okay, that's what like 5,
No, that's right, that's it. Well, it's a little more complicated than that. If it were 1/5, this would be right.
This is expandable.
But it's to the -5 power,
So
which is,
whenever you, that's the same thing, right?
no, let me explain. So, if I have x to the -1,
Are you already done?
that's 1 over x.
I'll like ask.
But if I have x to the 1 over n, that's the entry. You see how we're in this category? So that means that this next step could, you're on the right track for sure. Log base 2 of x plus 1 is -5. And then you could write that term as log base 2 of 1 over x plus 1 to the 5th.
I see, because it's attached to that stuff.
Uh-huh.
And then you just, and you do like plus 6x cubed.
Yeah, you're skipping a step, so be careful with that, but it's plus log base 2 of 6x cubed. That would be the logical next. And then you would combine them using the product.
Okay.
So what you're gonna wind up with is this, and it's 6x cubed over that. 6x quantity cubed, which is 216. You're welcome. Yes, sir.
How am I getting started on this one?
So the very first thing you want to do is rewrite all those terms. So log base 13 of 6, plus log base 13 of cube, plus log base 13 of cube, plus log base 13 of 6. Okay.
I'm a little confused on why it's not.
Okay, so the, this is still plus at this point. So what we're gonna do is rewrite this like so. And then this one. Six cubes. Pretty sure, let me double check myself. So I'm gonna rewrite this now using the product property.
Okay,
So you got everything but that last step, basically.
okay, thank you.
You're welcome. All right, so let me help you with these real quick, because otherwise I'm afraid we're gonna run out of time. These lessons can get kind of lengthy here in the second half of chapter 3. So just giving myself some room to work here. So for this one, and again, I'm gonna go through these real quick, but you just compare your work to mine. So I'm going to rewrite 6 as 2 times 3. And then I'm moving out the exponents as coefficients. Okay, so that's the first one. That big old long mess. Then for the second one, something to me is less satisfying about expanding. I don't know why. Condensing is more satisfying. So this is log base 2 of x plus 1 to the negative 5 plus log base 2 of 6x cubed. And there's a really common mistake here. So a lot of people would write this as 6x cubed. It's not, it's 6 cubed x cubed. So be careful when you have the power of a product, the power goes to both factors. So it's 6 cubed x cubed. All right, so there's log base 2, and I'm going to rewrite this like so. And then one last application of the product property. In the condensing direction. So 216x cubed over x plus 1 to the 5th. I would in general not expect you to expand something like this. So you can always assume that it's okay to leave it in factored form, unless I specifically say otherwise. Okay. So change of base rule. Remember I told you guys I was going to give you an algebraic trick if you watch the video that allowed you to write any logarithm in your calculator. Well, here is the trick. The change of base rule. So if I have log base b of x, that's equal to log of x over log of b. You can use natural log as well, it doesn't matter. Any log of the argument over any log of the base. So for example, if I wanted to write log base 3 of x in my calculator, I would write that as common log x over common log 3. And if I wanted to graph this, I would punch this into the y equals screen. If I wanted to find log base 5 of 21, that would be the common log of 21 over the common log of 5. So any logarithmic expression can be written in terms of the common log or the natural log. I just use the common log, but it doesn't matter which of those you choose. I have noticed among people with graduate degrees in mathematics, the natural log is a little more ubiquitously used. I'm not sure why. This is called the change of base rule. The change of base. All right. So let's evaluate this expression. Needs to give us some values here. All right, so instead of what's written there, we're going to evaluate the following. Log base 3 of 5. And then also log base 1/2 of 6. So this is going to be the log of 5 over the log of 3. And the calculator will give us an approximation. So that's about 1.46 to the nearest hundredth. And then over here, the log of 6 over the log of 1/2. Negative 2.58. Approximately. And that's using the change of base rule. So you can now do any of these on your calculator. See why I held this back on that first section? You would have just plugged it in the calculator and that would have been that. Okay. So just really quick, I'll show you how that logarithm is used to determine the age of a sample. And this represents radioactive decay of an isotope. You know, you start out with 100% of the ratio you find in nature, but once an animal stops interacting with the environment, it stops taking in that radioactive element, and the radioactive element that exists within the carbon in that creature's body starts to all decay to the stable form. And so you find it becoming a higher and higher ratio of stable form to isotope. The isotope is extremely rare. In the case of carbon-14, it's created in the upper atmosphere by the sun's rays striking the stable carbon atoms in the upper atmosphere. And it works out to be about 1 in a trillion. So about 1 in a trillion carbon atoms in your body is carbon-14. But once you die, it starts to decrease. That ratio is already tiny, but it starts to become even less. Even 1 out of a trillion, it decreases from there. But anyway, a chemist determines a sample of petrified wood has a carbon-14 decay rate of 6 counts per minute per gram. What is the age of the wood in years? So the decay rate in fresh wood is 13.6 counts per gram, and the half-life of carbon-14 is 5,730 years. So first step is to determine the decimal fraction of carbon-14 remaining. So we would expect 13.6 counts for a very new piece of wood, and we get 6 counts. So this is the emission of an alpha or a beta particle from the carbon-14 as it decays to a carbon-12. I don't know if you guys have had chemistry yet, but when a radioactive isotope decays, it emits an alpha or a beta particle, or in some cases a gamma if it's a really big atom like a plutonium atom or something like that. But alpha or a beta particle, which is just protons and neutrons. So it sends those out, and those are what the Geiger counter picks up. And so if it's picking up this many, that's about 44% of what we would expect from a new piece of wood. So the question now is, how many half-lives is 44%? Well, it's about 1.18, and then we multiply that by the half-life of the element in question, which is 5,730 years, and the result's about 6,765 years. You don't have to write this down. I just wanted to show you how this might be used. Questions about anything we've discussed today? All right. In that case, I would like for you to complete the following. Page 185, numbers 2, 4, 10, 12, 18, 30, 32, and 59. So you see some fossils here. So in Northern Europe, there was an ancient cult that nobody's really sure exactly what their religion was. It was lost to history. Probably the builders of the Stonehenge were people that participated in this religion. But one of the things they would do is they would sink virgins in the bog. So they would take young women and they would sink them into a wet, marshy swamp where their bodies were extremely well preserved. And so now we can use carbon-14 dating to tell exactly how old these fossils are. And we find, they're usually about 8,000 to 10,000 years old. So very old indeed. The bog people of Northern Europe, they would sacrifice virgins to their bog god. Aren't you glad you didn't live back then?